Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again after months of spouting gibberish.
Despite decades of exploring the solar system, humanity continues to uncover astonishing discoveries. For years, we believed we had identified all the planets, until new evidence proved otherwise. But what about the Voyager probes? How far have they ventured beyond our solar system? Even scientists are amazed by the groundbreaking insights these spacecraft have revealed. One of the most fascinating discoveries is that our entire solar system, including the distant Oort cloud nearly a light-year away, is encased within a vast cosmic bubble. This enormous structure spans an incredible 1,000 light-years, with the Sun positioned near its center. But what happened when the Voyager probes crossed the edge of our solar system? Could we actually be enclosed within this immense space bubble? And how does this revelation reshape our understanding of the solar system structure? Let's dive into the answers. On September 5, 1977, NASA's Voyager 1 spacecraft launched from Cape Canaveral, Florida, aboard a Titan Centaur rocket just weeks after Voyager 2's launch on August 20th. Originally designed for a 5-year mission to study the outer planets, these resilient probes have surpassed all expectations, continuing to send data back to Earth more than 44 years later as they venture into interstellar space. The Voyager missions capitalized on a rare planetary alignment that occurs once every 107 years, allowing the spacecraft to perform gravitational slingshots from one planet to another, conserving their limited fuel. Despite launching second, Voyager 1 was the first to reach Jupiter and Saturn, focusing on these planets, while Voyager 2 explored Jupiter, Saturn, Uranus, and Neptune. Over a decade, the data transmitted by the Voyagers have profoundly shaped our understanding of the outer solar system, earning their place in textbooks and media alike. As a unique touch, each spacecraft carries a golden record, a time capsule of Earth sounds and music intended to communicate with potential extraterrestrial life. As of January 2024, Voyager 1 is approximately 14.9 billion miles from Earth, 158 times the distance between our planet and the Sun, cementing its status as the most distant human-made object in space. Voyager 2 achieved a major milestone in November 2018, becoming the second spacecraft to enter interstellar space after Voyager 1's groundbreaking departure in August 2012. Voyager 1's passage beyond the heliosphere, a vast region shaped by the Sun's charged particles, was confirmed when its plasma wave instrument detected a strong solar eruption between April 9th and May 22nd, 2013. This eruption caused nearby electrons to oscillate, leading researchers to determine that electron density outside the heliosphere was significantly higher than within it. These findings revealed a stark contrast. While interstellar space is denser than areas near the Sun, the outer edge of the heliosphere is much less dense than regions closer to Earth. By analyzing this data, scientists pinpointed Voyager 1's official entry into interstellar space to August 25, 2012, using electron oscillation measurements and observations of charged solar particles. Voyager 2 followed suit, crossing into interstellar space 6 years later, confirming the profound scientific significance of these twin spacecraft. The data from the Voyager spacecraft reveal many similarities, such as the overall density of particles encountered in interstellar space. However, their journeys revealed notable differences, sparking new questions about the Sun's trajectory through the galaxy. Outer space continues to defy our expectations, and Voyager 2's observations as it crossed the heliopause provide even more insight into this vast and mysterious frontier. The boundary between the heliosphere and interstellar space is unlocking some of the solar system's greatest secrets. To fully grasp Voyager 2's groundbreaking findings, it's essential to first understand the Sun's dynamic nature. Despite its seemingly calm exterior, the Sun is a colossal nuclear reactor hurtling through the galaxy at approximately 450,000 kilometers per hour. Its surface is an intricate web of magnetic fields that produce a continuous flow of electrically charged particles, known as the solar wind. This solar wind spreads outward in all directions, carrying the sun's magnetic influence across vast distances. Eventually, it encounters the interstellar medium, a region filled with remnants of ancient stellar explosions. Much like oil and water, the solar wind and interstellar medium resist mixing, creating a well-defined boundary called the heliosphere. This vast bubble, powered by the solar wind, extends roughly 11 billion miles from the sun, encapsulating the sun, all 8 planets, and a significant portion of the solar system's outer regions. Strange, isn't it? But it's the kind of strangeness that works in our favor. The heliosphere acts as a protective shield, guarding everything inside, including us, from the galaxy's most dangerous radiation. Without it, life as we know it would be exposed to potentially catastrophic hazards. The outer edge of the heliosphere, called the heliopause, marks the beginning of interstellar space. Understanding this boundary has profound implications for comprehending the sun's movement through the galaxy, as well as the conditions around other stars scattered across the cosmos. Scientists are especially intrigued by the interactions at this threshold, how the solar wind and interstellar medium mix, the extent of material exchange across the boundary, and the dynamics of this cosmic collision. When Voyager 1 passed beyond the heliopause in 2012, it provided the first direct insight into this mysterious region. However, interpreting its data was challenging. Scientists discovered that the interstellar magnetic field was 2 to 3 times stronger than expected, suggesting that interstellar particles exert up to 10 times more pressure on the heliosphere than previously believed. However, Voyager 1's data was incomplete due to the failure of its plasma instrument in 1980, resulting in gaps in the findings. In 2018, Voyager 2 provided a crucial breakthrough. With its plasma instrument fully operational, scientists obtained a clearer picture of the heliopause. As the spacecraft neared the boundary, they observed that the surrounding plasma slowed, heated up, and became denser, revealing key details about this critical interface. Beyond the heliopause, the interstellar medium was found to be far hotter than expected, with temperatures reaching at least 54,000 degrees Fahrenheit. However, because the plasma is extremely thin and diffuse, the overall temperature around the Voyager probes remains very low. Voyager 2 also confirmed that the heliopause is a porous boundary, allowing particles to move in both directions. For instance, Voyager 1 encountered 10 streams of interstellar particles that pierced the heliopause, much like tree roots pushing through rock before fully breaking past the boundary. In contrast, Voyager 2 detected a faint flow of low-energy particles extending over 100 million kilometers beyond the heliopause. As Voyager 1 neared this boundary, the outgoing solar wind slowed significantly, creating an eerie state of limbo. Meanwhile, Voyager 2 observed a distinct transitional layer in the solar wind, similar in width to the stationary zone recorded by Voyager 1. These differences highlight the intricate nature of the heliosphere and emphasize the need for more data to decode its complexities. The solar system proves to be as dynamic as a chameleon, presenting mysteries that call for a deeper understanding of the heliosphere. Voyager 1 exited the heliosphere at its leading edge, encountering the interstellar medium, while Voyager 2 departed through the left flank. However, the heliosphere's wake remains unexplored, leaving its overall shape uncertain. It could be spherical due to interstellar medium pressure, or it might have a comet-like tail, or even a glass-like form. Unfortunately, current spacecraft won't provide definitive answers. NASA's New Horizons, though fast, will lose power in the 2030s, still over 1 billion miles short of the heliopause. This limitation has fueled calls for a follow-up interstellar mission, a multi-generational effort to explore the outermost reaches of the solar system and beyond. With data from only 2 points, our understanding of the heliosphere's structure remains incomplete, making additional data crucial. Beyond the heliopause, Voyager 1 encountered a fascinating phenomenon, a continuous hum. As it crossed into interstellar space, its plasma wave instrument detected oscillations in the interstellar gas triggered by solar activity. Yet, between these bursts, it also registered a faint, steady signal. In 1 billion years, the Voyager probes will have traveled far beyond the solar system, drifting endlessly through interstellar space. By then, their instruments will have long fallen silent as their power sources deplete, leaving them as mere relics of human ingenuity.